So, if I told you that the last time you dropped your phone didn't just fall to the ground, but it actually like actively pulled the entire planet Earth up towards it,
Right.
you would probably think I'd completely lost my mind. Or if I told you that as you are sitting there right now, listening to this, seemingly perfectly still, you were actually locked in this violent, high-stakes physical battle just to remain in your chair.
Yeah, it sounds like science fiction.
It really does. But today, we are going deep into some foundational physics material that proves these invisible, chaotic interactions are happening around you every single second of your life.
It's a profoundly counterintuitive way to view the world, honestly. We are so accustomed to the mundane reality of things just sitting where we leave them, right? We're moving when we push them, that our brains actively filter out the sheer mechanical complexity of those
We
events.
just take it for granted.
We do. And for thousands of years, the brightest human minds looked at a rock resting on the ground and assumed it was just, doing nothing. They assumed nothing was the default state of the universe.
Which is exactly why the material we're diving into today is so exciting. We are looking at the fundamental principles of how forces affect motion. We're completely stripping away the intimidating equations and just looking at the raw mechanics of reality.
Yeah, we're going to unlearn centuries of bad intuition today.
Exactly. Unlearn it all to see the invisible rules governing everything from a coffee cup on your desk to the orbit of the moon. So let's start with the absolute baseline. Before we can talk about how things move, we have to define the invisible ghost causing the movement, right?
Right.
What actually is a force? Because in daily life, I use that word to describe like my willpower to get out of bed or maybe a really strong wind.
Yeah, and in physics, the definition is incredibly stripped down and specific. You have to forget willpower or some mystical energy. A force at its mechanical core is simply a push, a pull, or a squeeze. That is it.
Just those three.
Just those three. Every complex physical interaction you have ever witnessed or experienced can be reduced to one of those three fundamental actions.
Okay, let's ground that a bit. If I kick a football sitting in the grass, I'm applying a push. My foot makes contact, transfers that push, and the ball goes from sitting still to, flying through the air.
Exactly. And it goes beyond just initiating movement, too. Think about a game of tennis. The ball is already moving toward you at high speed.
Right.
When you swing your racket and strike it, you are applying a new push. That force doesn't just make the ball move, it completely violently alters the ball's existing direction and speed.
Oh, right. Because it was going one way and now it's shooting back the other way.
Precisely.
What about the squeeze part of the definition, though? Because a push or pull implies moving something from point A to point B.
Well, squeezing is just as crucial because it illustrates that forces can alter the physical architecture of an object. If you take a lemon in your hand and you squeeze it, you are applying forces inward from multiple directions. The lemon doesn't fly across the room, but its cellular structure physically deforms.
Skin ruptures, the juices are forced out.
Right. Deformation is direct evidence of force, just as much as a football flying through the air.
That makes total sense. So we have pushes, pulls, and squeezes.
Yeah.
But the material stresses that just calling it a push isn't really enough to accurately describe what's happening. There are two mandatory ingredients you need to define a force,
Yes. You cannot accurately describe a force without establishing its magnitude.
meaning its sheer strength, right?
Right. Its strength and its direction. Physics treats force as a vector quantity. To understand why direction matters just as much as strength, imagine you are trying to close an open door. You apply a push with a certain magnitude toward the door frame, and it clicks shut.
But if I apply that exact same magnitude of push to the door, but I direct it toward the hinges instead of the frame, the door doesn't close. I just stress the metal hinges.
Exactly. The amount of effort was identical, but the directional shift completely changed the physical outcome. Alter either the magnitude or the direction, and the consequence of the force transforms.
Here is where my brain starts to struggle with this, though. I mean, I can measure a piece of wood with a tape measure because it has physical dimensions, right? I can measure water in a measuring cup. How do scientists actually measure a push or a pull? It's invisible.
That's a great question. We measure the invisible by observing its physical consequences on something highly predictable.
Okay.
The standard unit of force is the Newton, named for Isaac Newton, of course. And to visualize how we measure it, the source material brings up a brilliant rudimentary piece of technology called a spring balance.
Oh, I remember those from middle school science class.
Yeah.
It's essentially a little metal cylinder with a hook on the bottom and a coiled metal spring inside.
Yeah, the spring is the key. That metal coil has a known constant resistance. If you hang a heavy rock from that bottom hook, gravity is applying a pull on that rock, dragging it downward.
Right.
As the rock goes down, it pulls the spring with it. The spring stretches in direct proportion to the magnitude of the gravitational force. You look at the little dial on the casing, and it tells you exactly how many newtons of force the Earth is exerting on that rock.
We commonly just call that weight.
Yes, weight is simply the measurement of gravitational force acting on mass, but you can use that same spring balance horizontally, too.
Oh, like pulling it across a table.
Exactly. If you attach the hook to a block of wood on a table and pull it with your hand, the spring stretches to reveal exactly how many newtons of force your muscles are generating to drag that block.
So we have our unit, the Newton. What really blew my mind in the reading, though, is the sheer scale of the forces happening around us constantly.
The range is astronomical.
It really is. It notes that a very light, almost imperceptible brush of a finger against your cheek generates about 1 millinewton of force. 1,000th of a newton.
And human engineering has progressed so far beyond what human nerve endings can even detect. Modern physicists operate experiments measuring forces down to the octanewton.
The yoctonewton, which, for context, is 10 to the power of negative 24 newtons.
It's unimaginably small.
Yeah, it's a decimal point followed by 23 zeros and a 1. It's an almost absurdly small number. If we took a single standard newton of force and scale it up so it was the size of the entire planet Earth, 1 yoctonewton would be smaller than a single grain of sand sitting on a beach somewhere.
That paints a perfect picture. We are attempting to categorize the mechanics that dictate the collisions of massive galaxies, all the way down to the subtle electromagnetic nudges between individual subatomic particles. It's a singular set of rules governing a vast spectrum of reality.
So, okay, we have our invisible pushes and pulls. We know they have direction and strength, and we know how to measure them. But the real world is messy, right? A football sitting in an empty void might only experience one kick. But on Earth, things are constantly being bombarded.
Constantly.
So what happens when multiple forces hit the exact same object at the exact same time?
We enter the concept of net force. In any natural environment, an object is basically a battlefield of intersecting pushes and pulls. To predict what an object will do, you have to add up all those interacting vectors to find the final resulting force.
The material uses a literal tug-of-war to explain this, which I think is great. Two teams pulling on opposite ends of a thick rope.
It's the perfect illustration of what we call balanced forces. Imagine the team on the left pulls with a massive magnitude of force. The rope wants to move left, but the team on the right digs their heels in and pulls the exact same magnitude of force to the right.
So the rope becomes incredibly tense, everyone is straining, sweating, but the knot tied in the absolute center of the rope does not move a single millimeter.
Because the forces are perfectly balanced. The 500 newtons pulling left are mathematically neutralized by the 500 newtons pulling right. The net force, the sum total of the interaction, is absolute zero.
Wow.
And when the net force is zero, the object's motion does not change.
But the moment someone on the right team slips in the mud, their magnitude drops. Suddenly, they're only pulling with, say, 400 newtons, while the left team is still pulling with 500.
And instantly, the forces become unbalanced. The math shifts. You subtract the weaker force from the stronger force. The rope now experiences a net force of 100 newtons. The direction of that net force points toward the left team, and the rope physically accelerates in that direction.
And this additive math works when forces push together too, right? Like I had a car breakdown a few years ago. I tried to push it from behind, but my singular force didn't have enough magnitude to get a 2-ton vehicle rolling.
Oh, heavy.
Yeah. But then a stranger pulled over, got behind the car next to me, and we pushed together.
Yeah.
Because we were pushing in the exact same direction, our individual forces stacked. My 300 newtons plus his 300 newtons created a combined net force of 600 newtons forward, which was finally enough to move the car.
That is the mathematics of motion in a nutshell. But, the concept of balanced forces actually reveals something deeply profound about the stationary objects around you right now.
What do you mean?
Well, we assume that if something isn't moving, there are no forces acting on it.
Right. Like my coffee cup sitting on my desk. It's just dead weight. It's doing nothing.
Far from it. The material presents this wonderful example of a basketball floating in a bucket of water. It sits there, perfectly still on the surface, not bobbing up, not sinking down. To our eyes, nothing is happening. But mechanically, it is a war zone.
Because gravity never turns off.
Yeah.
The Earth is constantly exerting a downward pull on the mass of that basketball.
A relentless downward pull. But the water in the bucket is not passive. Liquid molecules are incredibly dense and active. As the basketball pushes down into the water exerts what we call a buoyant force. Trillions of water molecules are physically pressing up against the curved rubber bottom of that basketball.
So because the ball is totally stationary, we can logically deduce that the invisible downward pull of the entire planet Earth is perfectly matched, down to the octanewton, by the upward push of the water in that bucket. The net force is zero.
It is a violent, dynamic equilibrium hiding in plain sight. Every stationary object you see is currently surviving a perfectly balanced onslaught of invisible forces.
Okay, I'm going to push back on this a bit because this brings up a massive paradox in my head. If balanced forces, meaning a net force of zero means zero movement and zero change, doesn't that mean you must constantly apply a new force to keep something moving? Like if I slide a wooden block across my desk, it moves for a second and then it stops. My daily lived experience tells me that things naturally want to be at rest.
You have just perfectly articulated the Aristotelian view of the universe.
Ollie.
Yes. Aristotle and essentially every educated human being for over 2,000 years looked at the world, saw exactly what you just described, and concluded that rest is the natural default state of all matter. They believed motion was an unnatural state that required a constant, continuous force to sustain it. Stop pushing the cart stops.
It seems like undeniable logic, right? How did anyone ever figure out that was wrong?
Because the world is full of invisible friction, which we will definitely get to, that ruins our observations. It took the genius of Galilei in the 17th century to realize that our everyday environment is deeply flawed for these kinds of observations.
So what did you do?
Well, Galileo couldn't build a vacuum chamber or travel to deep space to test his ideas, so he used incredibly rigorous thought experiments to basically strip away the environmental noise.
What was the thought experiment that finally broke Aristotle's 2,000-year streak?
Galileo asked people to imagine a horizontal plane, a surface made of a hypothetical material that is flawlessly, perfectly smooth, no microscopic bumps, no dust, absolutely zero resistance. Then he imagined a perfectly hard, flawlessly spherical ball.
So he's mentally deleting all the messy, real-world variables?
Completely. He reasoned that if you rolled this perfect ball down a slight incline, it would speed up. If you rolled it up an incline, it would slow down. But what if you rolled it along that perfectly flat, perfectly smooth horizontal plane? There is no incline to speed it up and no resistance to slow it down. What does the ball do?
If there's literally nothing to stop it, it would just roll forever.
Forever. Galileo realized that slowing down is not an inherent property of objects. Stopping is not a natural desire of matter. Stopping is an event caused by invisible forces interacting with the object. If you remove all external interference, if the net force remains absolutely zero, an object in motion will simply continue in motion into infinity.
That is a staggering paradigm shift. It means the coffee cup sliding across my desk doesn't stop because it wants to rest. It stops because it's being actively murdered by invisible forces.
Exactly. And this realization became the absolute bedrock for Isaac Newton. He formalized Galileo's thought experiment into what we now know as Newton's first law of motion, published in his 1687 masterwork, the Principia.
The phrasing of the first law is so famous. An object at rest remains at rest, and an object in motion continues to move with a constant velocity unless acted upon by a net external force. But I want to focus intensely on those two words, constant velocity, because I think people hear velocity and just think speed.
And that is a critical error. In physics, velocity is a vector. It contains two distinct pieces of information, the speed of the object and the specific direction the object is traveling.
So if constant velocity means neither of those things can change without a force, that means that if I see something turn a corner, even if it doesn't slow down, a force must be acting on it.
Absolutely. Consider a car driving around a perfectly circular racetrack. The speedometer might be locked at exactly 60 miles per hour the entire time. The speed is constant. But because the car is constantly curving, its direction is constantly changing.
Right.
Therefore, its velocity is changing every fraction of a second. According to the first law, an object can only change its direction if an unbalanced net force is actively yanking it.
In the car's case, it's the friction of the tires pulling the massive weight of the vehicle inward toward the center of the track.
Yes. If the track suddenly turned into frictionless ice, the car would not continue in a circle. The tires would lose their grip, the inward force would vanish, and the car would instantly slide off the track in a perfectly straight line at 60 miles per hour. An object's deepest, fundamental physical desire is to keep doing exactly what it's doing in a perfectly straight line forever.
And Newton gave a specific name to this stubborn, lazy quality of matter, right?
He called it inertia. Inertia is the inherent resistance of any physical object to any change in its state of motion. The larger an object's mass, the more inertia it possesses.
So mass dictates the laziness.
Exactly. A pebble has very little inertia. You can easily flick it to change its velocity. A freight train has massive inertia. It requires the enormous force of specialized brakes applied over a mile of track just to change its velocity to zero.
Okay, conceptually, I am entirely sold on Galileo and Newton. But let's bring this back to reality. Galileo's perfectly smooth plane does not exist. When I stop pedaling my bicycle, something physically grabs my tires and drags me to a halt. We mentioned the word earlier, but we really need to dissect the invisible forces that constantly ruin our first law experiments on Earth.
We live in an environment completely saturated by two pervasive, unavoidable forces: friction and the normal force. Let's tackle friction first because it is the ultimate saboteur of motion.
Okay, so if I push a heavy wooden box across a concrete floor, it takes a ton of effort. Why? I mean, concrete looks flat to me. Wood looks flat.
They appear flat to the naked eye. But you have to imagine what those surfaces look like at a microscopic, almost atomic level. If you zoomed in on the bottom of that wooden box and the top of the concrete floor, they wouldn't look like flat plains. They would look like jagged mountain ranges colliding with deep, cavernous valleys.
So when I push the box, those two microscopic mountain ranges are basically grinding into each other.
Yes. The jagged peaks of the wood get physically locked into the valleys of the concrete. Atoms form temporary, weak electromagnetic bonds with each other. Friction is the collective force required to violently break all of those microscopic bonds and shear those mountain peaks off so the surfaces can slide past one another.
Wow, that sounds exhausting just to describe.
Mhm.
So when I give the box a really hard shove, my pushing force is greater than the friction force. The net force is forward, and the box accelerates. But the instant my hands leave the box,
The instant you stop pushing, your forward force drops to absolute zero. But the box is still moving forward, sliding over those microscopic mountains. Therefore, the friction force is still actively pushing backward, resisting the slide.
so the net force immediately flips.
Precisely. Now you have a net force pushing backward against the motion. According to the first law, an unbalanced force changes velocity. The box decelerates rapidly and grinds to a halt. The universe didn't want the box to stop. The microscopic mountains on the concrete physically battered it into submission.
But friction relies on the two surfaces pressing against each other, which brings up the second invisible force you mentioned, the normal force. If gravity is constantly pulling the heavy box down, why doesn't it just crush the microscopic mountains and fall straight through the concrete floor to the center of the Earth?
Because the floor is not empty space, it is made of densely packed atoms. When gravity pulls the box downward, the electron clouds of the atoms in the bottom of the box are pushed incredibly close to the electron clouds of the atoms in the concrete floor.
And electrons have negative charges.
Right, and negative charges violently repel each other. This immense microscopic electromagnetic repulsion pushes upward against the box. We call this the normal force. In geometry, normal simply means perpendicular. It is the force that a surface exerts perpendicular to itself to prevent solid objects from passing through each other.
So vertically, the massive gravitational pull of the Earth downward is perfectly exactly matched by the normal force of the concrete floor pushing upward. The vertical net force is zero. The box doesn't float into the sky, and it doesn't sink into the basement.
And this normal force directly impacts friction too. The heavier the box, the stronger gravity pulls it down. To compensate and keep the box from falling through the floor, the normal force must push up equally hard. This intense squeezing pressure forces those microscopic mountain ranges deeper into each other, massively increasing the friction.
Okay, so if friction is this constant microscopic grinding that ruins motion and steals energy, wouldn't the world be an infinitely better, highly efficient place if we could just magically eliminate all of it?
It is very tempting to view friction as a nuisance. But the material offers a brilliant counter-perspective on this. If you eliminated friction, human civilization and virtually all terrestrial life would instantly collapse. You couldn't even walk to your kitchen.
Wait, really? Walk me through the actual physics of taking a step. because we do it millions of times and never think about the mechanics.
Think about the precise movement of your leg when you walk. You don't just lift your foot and let gravity tip you forward. To propel your mass forward, your foot has to strike the ground and physically push backward against the floor.
Right. If I want to walk straight north, my foot is actually pushing south.
If there were absolutely no friction, your foot would simply shoot backward. The microscopic mountains wouldn't catch. You would be like a cartoon character slipping on a banana peel, endlessly running in place and falling on your face. Friction is the crucial anchor. When you push your foot backward, the friction force violently grips the sole of your shoe, preventing it from sliding.
This makes perfect sense when you look at the bottom of running shoes or hiking boots. They aren't flat. They're covered in deep rubber grooves and intricate patterns. We are intentionally designing footwear to maximize the jaggedness of our microscopic mountains to guarantee friction.
Yes, exactly. The tires on a car operate on the exact same principle. The heavy engine spins the tire attempts to push backward against the asphalt. The intense friction between the rubber tread and the road grips the tire, and that interaction is what actually propels a 2-ton vehicle forward at highway speeds.
And this totally explains the pure terror of walking in slippery socks on a highly polished floor or driving on black ice. The water or the ice fills in all those microscopic valleys, creating a temporary, ultra-smooth surface.
Right, the friction drops to near zero.
You push backward to walk, there's nothing to grip, and you go down. Friction isn't the enemy of motion. It's the prerequisite for controlled motion.
It is the great paradox. The force that stops things from moving is the exact same force required to start things moving in the first place.
All right, so we've established the rules of the first law. If forces are perfectly balanced, nothing changes. But that leaves a glaring question. When the forces are unbalanced, we know the object's velocity will change. It will accelerate. But how much? Like if I push a boulder with 500 newtons of force, how do I calculate exactly how fast it will move?
This is where Newton elevated physics from philosophical observation into hard predictive mathematics. He didn't just tell us that unbalanced forces cause acceleration, he gave us the exact formula to calculate it. This is Newton's second law of motion.
And it gave us arguably the most famous equation in classical physics, F equals ma. Force equals mass times acceleration.
It is an equation of profound, elegant simplicity. It establishes two incredibly intuitive, proportional relationships that govern the universe.
Let's break those down, starting with mass. Imagine I am at the grocery store. I have two identical shopping carts. One is completely empty. The other one is loaded to the brim with heavy cases of bottled water. I stand behind the empty cart and give it a firm push. Let's say 50 newtons of force.
The empty cart has very little mass. Therefore, according to the first law, it has very little inertia. It puts up almost no resistance to your push. So that 50 newtons of force causes massive acceleration. The cart zips rapidly down the aisle.
Then I walk over to the cart filled with water. I apply the exact same 50 newton push.
The loaded cart has enormous mass, which means enormous inertia. It stubbornly resists any change to its state of rest. Your 50 newton push barely overcomes that resistance. The cart groans forward slowly, accelerating at a tiny fraction of the rate of the empty cart.
So the second law dictates that acceleration is inversely proportional to mass. If you apply the same force, a massive object accelerates slowly and a light object accelerates quickly. That feels like common sense. What about the other half of the equation, the relationship between force and acceleration?
Let's return to your empty grocery cart. You push it with 50 newtons and it accelerates at a specific rate. Now, what if you did your heels in and push it exactly twice as hard? You apply 100 newtons of force.
Well, because the mass of the empty cart hasn't changed, pushing it twice as hard means it will speed up exactly twice as fast.
Precisely. Acceleration is directly proportional to the net force applied. Double the force, you double the acceleration. Cut the force in half, the acceleration drops by half. And crucially, the direction of the object's acceleration will always perfectly align with the direction of the net force pushing it.
And this brilliant little F equals ma equation is actually how scientists mathematically define the Newton, isn't it? The unit we talked about earlier.
Yes, the metric system is a beautifully interconnected web. Let's say you have an object with a mass of exactly 1 kilogram. You want to apply a push to that object so that it accelerates by exactly 1 meter per second every single second.
Meaning after 1 second, it's moving 1 meter per second. After 2 seconds, it's moving 2 meters per second.
Exactly. The precise amount of mechanical force required to make that 1 kilogram mass accelerate at that exact rate is strictly defined as 1 newton. 1 kilogram multiplied by an acceleration of 1 meter per second squared equals 1 newton.
It makes the math so incredibly clean. But the material we are diving into adds a slight wrinkle to this. F equals ma is perfect for shopping carts and wooden blocks because their mass stays consistent. The block doesn't magically lose half its wood while sliding.
Right. But in the cosmos, mass is not always constant. And if mass is changing, F equals ma begins to break down as a predictive tool.
The classic example is a spacecraft. A massive Saturn V rocket sitting on a launch pad is overwhelmingly just a giant container of highly explosive liquid fuel.
When the engines ignite, the rocket generates millions of pounds of upward thrust. But simultaneously, it is violently ejecting thousands of kilograms of burned fuel out the back nozzles every single second. The rocket is rapidly becoming lighter. Its mass is dropping drastically.
So if the m in F equals ma is constantly shrinking, you can't just use simple algebra to predict how fast the rocket will accelerate.
You cannot. Which is why Newton's deeper, more robust formulation of the second law relies on a concept called momentum.
Momentum is essentially how much oomph a moving object has. The formula is just the object's mass multiplied by its current velocity. A massive speeding freight train has terrifying momentum. A slow-moving housefly has almost zero momentum.
Correct. And Newton stated that force is actually equal to the rate of change of momentum. If you push an object, you are altering its momentum over time. For a grocery cart, the mass is locked, so the only way its momentum can change is if its velocity changes, which is standard acceleration.
Right.
But for a rocket ship, both its mass and its velocity are changing simultaneously. Calculating the rate of change of momentum allows orbital mechanics engineers to perfectly predict the trajectory of a spacecraft, even as it constantly sheds tons of weight into the atmosphere.
That is incredible. So F equals ma is the incredibly reliable shorthand we use for terrestrial daily life, but momentum is the master key for complex dynamic systems.
It is the deeper truth behind the simplified equation.
Okay, we've covered the first law: objects are inherently lazy and resist change. We've covered the second law, the math of how hard you have to push to overcome that laziness. Now we arrive at the third law. And to transition, I want to point out a flaw in how we have been talking about this so far.
Okay, what flaw?
Every example we've used treats forces like a one-way street. A foot actively kicks a passive ball. A person actively pushes a passive cart. We're treating the universe like an active participant bullying passive objects.
And this is perhaps Newton's most profound realization. That entire framework is an illusion. There is no such thing as an isolated singular force anywhere in the universe. Forces cannot exist alone. They are intrinsically, unavoidably an interaction between two distinct entities.
This brings us to Newton's third law of motion. Whenever object A exerts a force on object B simultaneously exerts an equal and opposite force on object A.
The famous shorthand is, for every action there is an equal and opposite reaction. But that phrasing often confuses people into thinking the forces cancel out. They don't cancel out because the forces are acting on two different objects. It is a mutual exchange.
Let's use the canoe example from the text to visualize this because it helps a lot. You are sitting in a canoe on a perfectly still lake. You want to move forward. You take your wooden paddle, dip it into the water, and you pull the paddle backward toward the rear of the boat.
Let's track the mechanics. Object A is the paddle. Object B is the water. The canoeist uses their muscles to make Object A exert a massive force backward onto Object B. You are physically shoving water behind you.
But according to the third law, the water cannot just passively accept being shoved. It must fight back.
Instantly and simultaneously. Object B, the water, exerts a force onto Object A, the paddle. The water pushes the paddle forward with the exact same magnitude of force that the paddle pushed the water backward.
And because my hands are holding the paddle and my body is sitting inside the canoe, when the water violently pushes the paddle forward, it pushes me and the entire boat forward across the lake.
Exactly. You do not propel the canoe by pushing the water. You propel the canoe by forcing the water to push you. It is the exact same dynamic we discussed with walking. You push the earth backward, the earth pushes you forward.
The material has another incredibly visceral example. Anyone who has seen firefighters struggling to control a high-pressure fire hose has seen the third law in action. Why does it take 2 or 3 strong people leaning their entire body weight forward just to hold a hose steady when the water is turned on full blast?
Because of the violent interaction happening inside the nozzle, the heavy mechanical pump on the fire engine is forcing water down the pipe. At the nozzle, Object A, the internal structure of the hose, exerts a massive focused force onto Object B, the water accelerating it forward out into the air.
The water pushes back.
with terrifying force. Object B, the water, simultaneously exerts an equal and opposite force backward onto Object A, the hose nozzle. The water essentially acts like a solid battering ram pushing violently backward into the hands of the firefighters.
Wow.
If they don't lean heavily forward, using the friction of their boots against the asphalt to generate an opposing forward force, the hose will violently throw them backward onto the ground.
It's a literal physical fight against the water's reaction force. But here's my question. The paddle physically touches the water. The firefighter's hands touch the hose, and the hose touches the water. Does this dance of pairs only apply to contact forces? Because we know non-contact forces exist, like gravity.
The third law is an absolute universal mandate. It applies equally to forces acting across vast distances without physical contact.
Okay, let's circle back to the very first thing I said in this deep dive. My crazy statement that dropping your phone pulls the Earth upward. Walk me through the physics of how that isn't a hallucination.
Let's use an apple falling from a tree. When the apple snaps off the branch, the immense mass of the Earth exerts a gravitational force on the apple, pulling it downward toward the soil.
Object A, the Earth, pulls Object B, the apple.
But the third law cannot be violated. Therefore, Object B, the apple, must simultaneously exert a gravitational force on Object A, the Earth. The tiny apple is actively pulling the entire 6 septillion kilogram planet Earth upward toward the sky. And crucially, the magnitude of the apple's upward pull is precisely equal to the magnitude of the Earth's downward pull.
If the upward force pulling the Earth is exactly as strong as the downward force pulling the apple, why don't I see the ground leap up to smash into the apple?
Because you have to synthesize the third law with the second law, F equals ma. We have equal forces, but we have wildly disproportionate masses. The apple has a tiny mass, so a small gravitational force applied to a tiny mass results in a massive, highly visible acceleration. The apple plummets rapidly to the grass.
But the Earth...
The Earth has an unimaginably vast mass. When you take that exact same small gravitational force, the pull from the apple, and apply it to the colossal mass of the entire planet, the resulting acceleration is infinitesimally small.
like unmeasurable.
Exactly. It is so small that human instruments cannot measure it. But mathematically, physically, undeniably, the Earth does accelerate upward to meet the falling apple, even if it is only by the width of a fraction of a single proton.
That is just awe-inspiring. It means every time I take a step, every time I drop a pen, I am subtly, imperceptibly shifting the entire planet. We are entirely interconnected through these mutual exchanges.
Every action in the universe is a conversation between masses.
Before we close out this journey, I want to pivot to a deeply practical application of everything we've discussed. The material includes a fascinating section that serves as a masterclass on how human beings have manipulated friction, tension, and normal force to perform seemingly impossible physical feats.
You are referring to the capstan equation, which is one of the most elegant engineering hacks in human history.
Yes. Let's set the stage. Imagine you have a massive, heavy bucket filled with sand. It weighs hundreds of pounds. It's attached to a thick rope. The rope is tossed over a high, rough-barked branch of a tree. You are standing on the ground, holding the loose end of the rope, trying to keep the bucket suspended midair.
If the rope just goes straight up, rests over the top of the branch, and comes straight down to your hands, you are essentially in a brutal tug-of-war with gravity. The friction of the rope resting on the top of the branch helps a tiny bit, but you are mostly supporting the raw weight of the bucket with your own muscle power. Your hands will burn, and you will eventually drop it.
But the text outlines a simple experiment. It says, take that loose end of the rope and wrap it just one single time completely around the circumference of that rough tree branch. A full 360-degree loop. Then hold the end.
And the result is astonishing. By adding just one complete wrap around the wood, the required physical effort drops dramatically. You can suddenly hold that massive 100-pound bucket suspended in the air with just a casual, one-handed grip.
But how does the physics of that work? My intuitive brain says, okay, if 1 inch of rope touching the branch creates a certain amount of friction, wrapping it around adds maybe 10 inches of contact. So the friction should increase linearly. It should be 10 times easier. But holding a 100-pound bucket with 2 fingers is an exponential decrease in effort, not linear.
Your intuition assumes friction behaves linearly, which it does on flat surfaces. But when you introduce tension around a cylindrical object, like a tree branch, the physics warp into an exponential feedback loop.
Dive into the microscopic mechanics of that feedback loop, because that's where the magic is.
Let's visualize the tension. The heavy bucket is pulling fiercely downward on one side of the rope. As that taut rope curves around the branch, that tension doesn't just pull along the length of the rope. The geometry of the curve forces the tension to pull the rope inward, violently crushing the fibers of the rope into the bark of the branch.
Ah, I see. It's dramatically increasing the normal force. It's pushing those microscopic mountains together with immense pressure.
Exactly. The tension creates massive normal force, which creates massive friction. But here is where the loop begins. That intense burst of friction at the top of the curve holds back a percentage of the bucket's tension. So as the rope continues an inch further around the branch, the tension is slightly lower.
But it's still tight enough to squeeze inward, creating more friction.
Yes, and that new friction holds back even more tension. The friction at any given point along the curve depends on the tension, but the friction also reduces the tension for the next segment of rope. Because it compounds continuously along the curve, the total friction force grows exponentially with the angle of wrap.
So by adding just one extra 360-degree loop, you aren't just adding a little more surface area. You are feeding that exponential loop, potentially increasing the total friction holding the rope by a factor of 20 or 30, depending on how jagged the bark is.
It is a stunning mechanical multiplier. And it is the exact physical principle that allows a single human deckhand at a commercial port to secure a multi-ton cargo ship being battered by ocean currents.
They don't use giant hydraulic clamps or anything.
No, they use a capstan, or a bollard, a thick steel cylinder on the dock. The deckhand takes the mooring line attached to the massive ship and simply wraps it 3 or 4 times around the steel cylinder. The exponential compounding of friction is so immense that the deckhand can stand there, holding the loose end of the rope with casual ease, while the friction generated by those few loops entirely arrests the momentum of a multi-ton vessel.
It really feels like magic, but it's just a profound understanding of the invisible rules we've spent the last hour dissecting. Let's take a breath and synthesize everything we've learned today. We started by looking at a seemingly boring, mundane world of coffee cups and parked cars, and we unmasked the chaotic, invisible vectors of pushes and pulls governing their existence.
We observed the cosmic tug-of-war of balance forces, realizing that stationary objects are merely surviving a perfect storm of equal pressures like the basketball fighting gravity and buoyancy.
We shattered Aristotle's ancient, intuitive myth that objects naturally desire rest. We traveled with Galileo to a perfectly smooth mental plane, discovering the profound laziness of matter known as inertia and the inherent desire of objects to maintain constant velocity forever.
We confronted the dual nature of friction, the microscopic mountains that act as the ultimate saboteur of motion, grinding boxes to a halt, but also serving as the fundamental anchor that permits humans to walk and cars to drive.
We decoded the elegant mathematics of Newton's second law, F equals ma, revealing how an object's mass stubbornly resists acceleration and how force dictates the exact rate of change, eventually scaling up to the complexities of momentum and rocket science.
We revealed the underlying symmetry of the universe through Newton's third law. We saw that forces are never isolated actions, but mutual, inescapable interactions, a violent dance of pairs governing everything from canoe paddles striking water to the gravitational embrace between a falling apple and the earth.
And finally, we saw how compounding those invisible forces can allow a single rope to hold back a ship. It is an incredibly comprehensive, staggeringly elegant framework. Newton's laws predict the motion of almost every single thing we interact with on a daily basis. They built our bridges, they fly our airplanes, and they mathematically charted the course that put human beings on the surface of the moon.
They are a triumph of human intellect, but they are not the end of the story.
And that is the exact provocative thought the material leaves us with and where I want to leave you today. Newton's laws are brilliant, but they are not perfect.
No, they are an approximation of reality that works flawlessly in the middle ground environment of human existence. But when you push the universe to its absolute, unimaginable extremes, Newton's elegant math begins to unravel.
The text points out that if you look at objects with incomprehensibly massive gravity-like black holes that physically warp the fabric of space-time itself, F equals my breaks down, it gives the wrong answers. You have to discard Newton and rely on Einstein's theory of general relativity.
If you accelerate an object until it approaches the speed of light, the rules warp again. Time slows down, mass becomes infinite, and Newton's formulas disintegrate. You need special relativity.
And if you zoom in the other way, past the microscopic mountains of friction, down to the unimaginably tiny realm of subatomic particles, Electrons and quarks don't act like Galileo's rolling balls. They seem to teleport. They exist in multiple places simultaneously, and Newton's certainty evaporates completely into the strange probabilities of quantum mechanics.
Newton gave us the rule book for our backyard, but the broader universe plays by different, wilder rules.
Which leaves me wondering, as you sit there right now, looking at the objects resting around you, deeply aware of the invisible pushes, pulls, normal forces, and friction, holding your immediate reality together, what other invisible rules are hiding just out of sight? What bizarre microscopic or cosmic interactions are happening right in front of us, completely unnoticed, just waiting for the next great mind to come along and finally make them visible?